In this video we review the FP2 work on partial fractions, and this extends the work from C4 to include denominators of the form ax plus b, cx plus d, ex plus f, and also denominators of the form ax plus b times cx squared plus d. So we need to recall from previous modules that px plus q over ax plus b cx plus d can be rewritten as a over ax plus b plus b over cx plus d, and then similarly for a similar expression for px squared plus qx plus r over ax plus b times cx plus d all squared. The two new cases that are introduced in FP2 are that px squared plus qx plus r over three linear factors, in other words over ax plus b, cx plus d, ex plus f, can be rewritten as a over ax plus b plus b over cx plus d plus c over ex plus f, and also that px squared plus qx plus r over ax plus b times cx squared plus d can be rewritten as a over ax plus b plus bx plus c over cx squared plus d. We will need, in the course of FP2, to express other functions of the form p of x over q of x, where p and q are polynomials where the degree of p is greater than, or indeed equal to, the degree of q. And if that's the case, we will need to use polynomial division as well as the method of partial fractions. You'll see some examples of that, perhaps, when you get on to the rational functions work. The method of partial fractions is particularly useful with integration examples, and the following results will often be needed. That the integral of a fraction, which can be written as the derivative of a function divided by the function, is the logarithm of the modulus of the function, and in particular that gives us a quick and easy way of working out the integral of 1 over ax plus b and also the integral of x over cx squared plus d. In the integration work on FP2, you will have found out that the integral of 1 over x squared plus a squared is 1 over a tan to the minus 1 of x over a, and one needs to remember the angles must be expressed in terms of radians. And finally, at this stage, we need to just remember that if we have an integral of the form 1 over cx plus d all squared, that can easily be handled just making use of a substitution u equals cx plus d. So let's now have a look at an example coming from the 2010 paper. So the function f is defined by f of x is 3x squared over x plus 2 x squared plus 2. We have to express f of x as a sum of partial fractions, and then we have to evaluate an integral relating to f of x. So, first part, we've got to express 3x squared over x plus 2 x squared plus 2 as a sum of partial fractions. So the partial fractions we're going to have are going to be something of the form a over x plus 2 plus bx plus c over x squared plus 2. If we multiply right across that expression by the common denominator, x plus 2 x squared plus 2, what we are really looking for is that 3x squared needs to be the same as ax squared plus 2 plus bx plus c times by x plus 2. If we start off by substituting in x equals minus 2, the left-hand side of this expression just gives us 12. And then on the right-hand side, we've got a times 4 plus 2, so that's 6a. And then the final term is bx, or b times minus 2 plus c times minus 2 plus 2, which is 0. So that final part of the right-hand side contributes nothing at all. So we have 12 equals 6a, which tells us that a equals 2. Now if we put x equals 0, then we obtain 0 on the left-hand side equals a times 2 plus c times 2. So we've got 0 equals 2a plus 2c. We know that a is 2, so that's 4 plus 2c must be 0, so c must be minus 2. Finally, we can look at the number of x squareds that we've got on both sides of this expression here. On the left hand side we've got 3 lots of x squared. On the right hand side we've got a lots of x squared here, and then we have b lots of x squared from double bracket here. So we must have 3 equals a plus b. We know that a is 2, so b must be 1. So we have that f of x is equal to 2 over x plus 2 plus 1 lot of x, take away 2 all over x squared plus 2. Moving on to the second part of the question then, we can say that the integral of f of x between 1 and 2 will be the same thing as the integral between 1 and 2 of 2 over x plus 2, add x over x squared plus 2, take away 2 over x squared plus 2. So let's have a think about each of the integral parts of the integral separately. 2 over x plus 2 can be written as 2 lots of the integral of 1 over x plus 2. 1 over x plus 2 is an exact example where we have the integral of the derivative of a function over the function itself. So we can say that that is just 2 lots of the natural logarithm of the modulus of x plus 2. X over x squared plus 2 is very close to being an integral of f dash over f. However, we really need 2x on top of the fraction. That's easily arranged. We can say that the integral of x over x squared plus 2 is the same thing as 1/2 of the integral of 2x over x squared plus 2. 2x is the derivative of x squared plus 2, so we can say that we have got 1/2 of the natural logarithm of x squared plus 2. And finally, we've got the integral of 2 over x squared plus 2. Well, we can pull the 2 on the numerator outside, so we've got 2 lots of the integral of 1 over x squared plus 2. That's a standard integral, so that is 1 over x squared plus a squared to be integrated, where a is root 2. So we're going to end up with 2 lots of 1 over root 2 tan to the minus 1 of x over root 2, which simplifies through to root 2 tan to the minus 1 of x over root 2. So we've managed to handle each of the terms inside the big integral here at the beginning separately, so we just need to put the results together. So 2 over x plus 2 integrated to give us 2 times the logarithm of x plus 2. X over x squared plus 2 integrated to give us 1/2 the logarithm of x squared plus 2. And then the 2 over x squared plus 2 integrated to give us root 2 tan to the minus 1 of x over root 2. If we insert the limits, we obtain 2 ln 4 plus a half ln 6, take away 2 tan to the take away root 2 tan to the minus 1 of root 2. Take away, when we put x equals 1 in, we obtain 2 ln 3, add a half times the natural logarithm of 3 minus root 2 tan to the minus 1, 1 over root 2. And then making use of our calculator, we've got 2.31745, take away 1.87611, which ends up giving us an answer of 0.441, correct to 3 decimal places. In terms of the marking for this question, part A received 4 marks, 1 mark for knowing how to split the partial fractions up, and then 3 marks for obtaining the correct values of A, B and C. And then for part B, evaluating the integral, first mark was for splitting the integral up into its 3 separate bits. Then there was an answer mark for handling each of those separate bits individually. So that was 3 answer marks, for each, 1 for each of the 3 parts of the integral. And then the last 2 marks were for correctly evaluating the definite integral. You will find the method of partial fractions occurs in the module FP2 not only specifically as partial fractions, but also as part of the work on sketching the graphs of rational functions, and also on the section of work on integration. So you will find us using partial fractions elsewhere in these revision videos.